Section 4.3, we're going to cover properties of logarithms. So basically we're going to look at the back of the properties of exponents, and we're going to basically use them as a reference, because those properties of logarithms, they come from the properties of exponents. Now the first property of logarithms is called the product rule, and we're going to make a reference to the product rule in exponents. So the product rule in exponents, if you remember, it tells you that if you have any base raised to a power and you multiply times the same base raised to another power, then you can combine them into one by adding the powers. Okay. Now in logarithmic forms, adding the powers, remember that every logarithm represents an exponent. So when I say add the powers, that in logarithmic forms, it means add the logs. That's what you see right here on this format. Okay, because remember that every log represents a power. So basically, when we say log base b of m plus log base b of n, means add the power for this log plus the power for this log. And that happens at the addition of the powers again when you have a product. So in other words, when you have the log base b of a product means a multiplication of two values that changes into an addition of two logs. The log of the first value in that parenthesis plus the log of the second value inside of that parenthesis. Now, the second rule, it is the quotient rule. That one states basically that when I have any base raised to a power and then I divide it by the same base raised to another power, then you are going to subtract the powers. So basically, subtracting the powers, if we look at it in terms of logarithms, it means subtracting the logarithms. So if I have a division at the log base b of a division right here, then we're going to subtract the logs, the log of the numerator minus the log of the denominator. And the last rule is called the power rule. This one states basically when we talk about exponents that when I have a base raised to a power and I raise that to another power, then you are going to multiply the powers. It is basically the same thing right here. When I have a log raised to a power, that's the same thing as saying that I have a power raised to a power, because remember the log represents a power. So that means that we're going to multiply the power. So this power that we have here, we multiply times the log, which represents the other power. So that's the same thing as saying that you're going to bring the power to the front and you're going to multiply it times the log. So these are the three basic properties of logs that we're going to be covering today on this section. Let's start with the following. Now we're going to use those properties for two things: to expand logarithmic expressions, that is one operation, and to condense logarithmic expression, that's the second operation. Now on this first part, we're going to be expanding logarithmic expressions. So basically what we want to do, using the product rule, the quotient rule, and the power rule, we want to split this log into several logs as much as possible. So this one, you see that there is a multiplication right here inside. So when I have a multiplication inside of the log, then this is the same as log base b of m times n, which is going to be the same as log base b of m, which is 343, plus the log base b of n, which is x. And this is basically the separation that we can use here. This is called the product rule. That's what we can see on this log. Now, one more thing that we need to try to do is, says where possible, we need to evaluate logarithmic expressions. Now, we cannot evaluate this second expression because that one contains an x. Now, the one that we could evaluate, it is the first log. Now, remember what we covered in the first part of the lecture on section 4.2. We learned how to evaluate logarithmic expressions. How do we do that? The 7 represents the base. This means that 7 raised to some power, it equals to 343. Now, if you can find an integer power of 7 that gives you 343, then you can evaluate it. If you cannot find an integer power, then you do not evaluate it. You leave it as is. Now, 7 to the second power is 49. 7 to the third power, 7 times 7 times 7, it's 343. So this log, the value of this log is 3, meaning that the power is 3. So this log is equal to 3. Okay, 3 plus, and then we bring down the second log, which is log base 7 of x. So this is my final result for this. So 3 plus log base 7 of x. Now we're going to continue doing the same thing. We're going to use the properties of logarithms to expand this expression next. So this log gives us natural log of e to the 5th power divided by 13. So we're going to do the same thing. So when I have a division in the log, then we have to separate it using the quotient rule. It tells me that the log of m over n is equal to the log of m, which is the numerator, minus the log of n, which is the log of the denominator, ln of 13, which is the denominator. And then what we have to do is we need to evaluate if possible. Now remember, when we talk about the natural log, that we can only basically evaluate it anytime we have e as the result, as the value. Because remember that the natural log works with the base of e only. So the only one we can evaluate is this one, and this is a special property. We covered it on section 4.2. When I have the ln of e raised to some power x, it is equal to x. ln of e just disappears from the expression. So ln of e raised to the power of 5, it is just going to be 5. So this expression is going to be 5 minus ln of 13. This is the answer for this expression in expanded form. The next one. Now we're going to be expanding this logarithmic expression here. Use the properties of logarithms to expand this logarithmic expression. And then evaluate, if possible, without using the calculator. So when we have a division, that is called the quotient rule again. So this is the same thing as saying we have the log of m, log base b of m over n, and that we're going to change it into a subtraction. It will be the log base b of m, which is the numerator, minus the log base b, which is 3, of n, which is the denominator. Okay. So there's two more things that we can do. One of them is that if you look at this log, we can evaluate it, and this one is very common, because this one means that 3 raised to what power, it equals to 27, and that would be 3 to the 3rd power. So this log right here has a value of 3. That's the power. And not only that, if you remember, we talked about the square root. The square root, in reality, it represents a power of 1/2. So then on this problem, we also have the power rule, which tells me that if I have a power on the log, very simple, you're going to bring the power to the front and multiply it times the log. So it will be 1/2 times the log base 3 of x, and then we bring down the minus 3. And this is the answer for this expanded form, for this problem. The next one. Now we're going to be expanding this logarithmic expression. So this one states, use properties of logarithms to expand again. We have the natural log of x cubed and the square root of x squared plus 3 over x plus 3 to the 6th power. Now, to expand this one, just keep in mind that this log has a division. I'm going to undo that division first. To undo the division, we're going to use the quotient rule, which states that the log of m divided by n equals to the log of m, which is the numerator right here, minus the log of n, which is the denominator. Now, what do we see right here on this first log? X cubed and the square root of x squared plus 3, since there is nothing in between, that's a multiplication. So we're going to use the product rule to separate or to expand this one. The log of m times n equals to the log of m plus the log of n, which is going to be written like this. And then we're going to put the other one, which is the minus the log of x plus 3 to the 6th power. Now you see that we have the power rule. The power rule tells you that you're going to bring the powers to the front. This power and this power, they're going to go to the front. So that's going to give us a 3 ln of x plus, now I'm gonna leave that pending, and at the end we have minus the 6 ln of x plus 3. Now I'm leaving the one in the middle pending because if you remember, there is a square root. And what does the square root basically represent? It represents a power of 1/2. So that means we also need to bring this power to the front. So my final solution for this expanded form is 3 ln of x plus 1/2 ln of x squared plus 3, and then minus 6 ln of x plus 3. This is a complete expanded form. Now, the next thing we're going to do is we're going to do the opposite operation. Now, what we're going to do in the next couple of problems is that we're going to use the properties of logarithms, but now we're going to condense. Condense means that we're going to put them back together into one single logarithm. That's the definition of condensing. And it tells you right here, condense the logarithmic expression, which means write as a single logarithm whose coefficient is 1, with no number in front of it. So just one single log. Okay. So on this problem, we got the log base 6 of 12 minus the log base 6 of 2. According to the definition, if I have a subtraction of two logs, we're going to combine it back into a division. Log base b of m minus log base b of n equals to the log base b of m divided by n. But that can be divided, so that gives you log base 6 of 12 divided by 2, which is 6. But now we can evaluate this. If you remember, this is a special property, because this means that 6 raised to what power equals to 6? That would be power of 1. Anytime we have a log base b of b, that is automatically, by definition, by the properties, it equals to 1. And so the answer for this log is just 1. Now, the next problem. Now we're going to condense this logarithmic expression. So, on this one, we have two things that need to be done. Number one thing is that we have the coefficients in front of the logs. Remember that those coefficients, in reality, they represent powers. So we're going to move those back to the as exponents. So that would be log base b of x raised to the 8th power. That's what this one is. Then plus log base b of z to the 6th power. And then we have one more property to use. When we have an addition of two logs, we're going to put them back together into one log, into a multiplication. So this is log base b of m plus log base b of n equals to log base b of m times n, which is my z to the 6th. I don't have to put the times symbol, so we can just leave it as log base b of x to the 8th power, z to the 6th power. This is going to be the solution for the expanded form of this. There's nothing that we can evaluate here because it all contains x variables, x's, y's, and also the basis of b. So we can only evaluate possibly if it is consisting of only numbers. So if the log is only numerical. Now, let's go to the next one. We are going to condense this log right here. Use the properties of logarithms to condense these logarithmic expressions. Where possible, evaluate logarithmic expressions. So we can do this in two ways here. We can put the exponent back to the top first, or we can condense these two. Now, I would rather put the exponent back to the top. Now, that 1/2, basically, since it is everything is in the parentheses with the 1/2 on the outside, that 1/2 in reality, it is the power of both the x and the y. So we can rewrite this like this. So it would be log base 2 of x raised to the power of 1/2 plus log base 2 of y raised to the power of 1/2. Now, but let's remember something. What does the power of 1/2 basically means? It means that this is the square root of x, plus log base 2 of y to the 1/2 means of the square root of y. What is the last thing we can do? Since there is an addition of two logs, then we can combine them using multiplication. That's the product rule. It states that the log base b of m plus the log base b of n equals to the log base b of m times n. But let's remember something we covered back in section P.3 in the radical section. The square root of x times the square root of y, it is going to be the same as the square root of x times y. And this is my final solution for this condensed version of this expression. Now we're going to do one more of condensing, then we're going to go to the end of the section. We're going to condense the following logarithmic expression, and where possible we're going to evaluate. Again, all of them consist of variables, so there is no evaluating is not a possible thing here either. Okay, so first thing we're going to do, let's go ahead and move the powers back to the top on this expression. So that 1/2 is going to be the power for both the x and the y, and that 4 is going to be the power for the x plus 7. So we're going to rewrite it like this. It would be the log base 3 of x to the 1/2 power plus the log base 3 of y to the 1/2 power minus the log base 3 of x plus 7 raised to the 4th power. But then let's remember one more thing. What does it mean by the 1/2 power? It means the square log base 3 of the square root of x plus log base 3 of y to the 1/2 power means log base 3 of the square root of y. And I'm just going to rewrite the other one. Okay. Now let's combine these logs right here. So on this one, there is an addition of two logs, so we can put it back together by multiplying them. So it would be the log base b of m plus log base b of n equals log base b of m times n. And then the minus log base 3 of x plus 7 to the 4th power. Now, also from the radical section, we talked about this one a while ago. When I have the square root of x times square root of y, that is going to be the exact same thing as the square root of x times y. Now, to complete this solution, there's only one more thing to do. Remember that when we have a subtraction, then we can combine them into a division. So this one tells me that the log base b of m minus the log base b of n equals to the log base b of m divided by n. And this is my final solution for this log. It is already condensed into one log. That was the reason, that was the idea behind these problems, to combine into one single log. Okay, so now we're going to go into the last part of the section. Now I'm going to show you basically how you can put the logs in the calculator. Okay, if you have a TI-83 or a TI-84, then this is how you put logs in the calculator. However, if you are using a TI Inspire, then that one you don't need to do this change. The Inspire allows you to put any base into the calculator. However, if you look at this calculator, which is a TI-83 or TI-84, the log that is programmed into the calculator only contains a base of 10. We cannot put a log with a different base in here. So what we can do is this. It is called the change of base formula, change of base property, which allows us to rewrite any log of any base into base of 10. And the formula says this: the log base v of m equals to the log of m, which is the log of the result, divided by the log of b, which is the log of the base. If we write it in this format, then you see that now there is no base on both of these logs that we created, and the base, that means that it is 10 and 10 for both. Also, you can there's another property that tells you that you can interchange it. So if you, instead of writing it as log of m divided by log of b, if I write it as natural log of m divided by natural log of b, then it's going to give you the same result if you use it into the calculator. So any of the logs that we did before, like the evaluating, you can evaluate them using that property. For example, this one. Take a look at this log that we did right in here. If you would like to evaluate it using the TI-83 or TI-84, then what you do is you divide the log of the result, which is 27, close parentheses, divided by the log of the base, and the base is 3. And if you press enter, that gives you the power, which is a 3. That's what we got here. Also, if you interchange it and instead of log, you use ln of 27, natural log of 27 divided by natural log of 3, it is still going to give us the same result. That's what the definition tells you. So we are going to answer the last question in this section, which is going to be this. What I want you to do is I want you to use either common logarithms, which is log, or natural logarithms, which is ln, in a calculator to evaluate this expression. So how do we put this in the calculator? There are two different ways in which we can evaluate it. The log base 16 of 15, you can write it as log of 15 divided by log of 16. Or you can write it as natural log of 15 divided by natural log of 16. Either way that you do it, it's going to give you the same result. So if we put log of 15 close parentheses divided by log of 16 close parentheses, we get 0.98 to 2 decimal places. Let's go ahead and round to 2 decimal places. It is going to be 0.98. If you also do it with the ln of 15 divided by ln of 16, that's also going to give us 0.98. So no matter what we use, either log or ln, when you're evaluating a logarithm into the calculator, both of them will give you the exact same result. And with this problem, we conclude section 4.3, which is about properties of logarithmic functions.